We're now going on to topic 3 of chapter 7, basic counting principles. And I see there's a little light shining there, so you may not see it too well. And the first thing we're going to look at is what is called the addition principle. Now here in college, there is a chemistry class. And as we look at that class, we see there are 13 males. From my biology days, that's the symbol for male, and 15 females. Give you a little bit of genetics on the side. So we say that set operations are useful in counting these members. So we'll have M stand for the male group, F for the female group, and what we're going to do is show a union of our male and female class members. And there are 28. 15 and 13 add up to 28. Now, if we, again, we're looking at set operations here. This is our intersection. So males intersect with females. Are there any? Not in this group. So that is an empty set. Now, how do we put this in the addition principle in set notation? Well, we're going to say our number of individuals of the union with our M and F set is equal to, and we see it right here. Let me just illustrate that. In a sense, we're distributing that, and we get this. We distribute that, and we get this. And then again, our M number is 13. Our F number is 15, which gives us our total. And you might say, well, we didn't have to make it this fancy. That was obvious. Well, again, we're going to get into some items that are more difficult as we move on. We just want to illustrate this. And keep in mind, the key word that Albert mentioned for our union is the word or, and the key word for intersection is and. These are very specific mathematical words that have other meanings in regular English, but here they have this meaning. In this next example, and again we're building up to some basic material here. Here we have a math class, and we do a count in this math class and find that there are 22 math majors. There are also 16 physics majors. But in this class, there are also 7 double majors. So again, how might a Venn diagram help us to see this? Well, again, the way to do it is to put your double major, that would be your area of intersection. So your total of math majors are 22, 7 of which are double majors. So how many math majors all by themselves? You just subtract the 7 from the 22, and that gives you 15. Okay, well, physics majors, there were 16, but again, 7 were double, so that left you with 9. 7 plus 9 is 16, 15 plus 7, 22. So how many students do you have then in this class? Well, it would be 15 plus 7 plus 9. Now, if you just counted your 22 and 16, that wouldn't give you an accurate count, because again, of the double majors. So what kind of formula might we come up with? And you want to perhaps see it in action. Well, we're saying that the number of students in union, your math and physics sets, would be the sum of the math students plus the sum of the physics students minus those that are in intersection. So looking at the math in some more detail, here we have 15 plus 7 plus 9 is 31. Again, if you see it laid out like this, this is what goes on in the background, but now let's use our formula. We're going to have the union of M and P, where there are 22 in our math group, 16 in our physics group, majors. But now, what is common between them, we have to subtract that. So our intersection, remember, there were 7 individuals. So if we go 22 plus 16, that's 38, minus the 7 in this group, that gives us our 31. So again, we don't always want to write it out in a Venn diagram. We want to be able to use a formula like this, and we want to see how this formula works. Moving on to example 1, we have in a certain city 750 firms offer health benefits to their employees. In that same city, 640 firms offer dental health care benefits. And also in that same city, 280 firms offer both dental and health care. I'm in that group because I have both. Okay, again, I'm not going to make a Venn diagram for everyone, but we'll see what's going on. So for health care, 270. Dental, 640. So you might ask, well, how many just have health care? How many just have dental care? And you would do that by putting your intersection here in the middle there, 280, subtract it from 640, and you get 360. Have just dental care. And do the same thing here. Subtract 280 from 750 and get 470. Now to find out how many are enrolled, it would be the combination of the union of these two minus the intersection, which is what I have down here. Or if you just add these 3 figures, they would give you the same thing. But this is the formula they're featuring. This is the union minus the intersection gives you your total number of firms with some sort of health coverage. In the textbook, they do go over Theorem 1, which is the formula we have been using, and also our first example when they were a disjointed set, that it's just the sum of set A and set B. When there is intersection, you subtract the point of intersection. Okay, now here's a market research that was done in a city in which there were two newspapers, the Sentinel and the Journal. And randomly they selected 100 individuals. Now this is your universal group. And they ask, do you read the Sentinel? And 35 individuals of this 100 said they did. And do you read the Journal? And 60 of those 100 individuals said they did. And they also asked, do you read both? And of that 100 individuals, 20 said they read both. So going back to our Venn diagram, this would be the 35 individuals that read the Sentinel, the 60 individuals that read the Journal, and then again the strategy in doing this is what you do is you put in your intersection first. That's your 20 individuals. So then you subtract the 20 from the 35, and that gives you the 15 that just read the Sentinel. And if you do the same thing on this side, subtract the 20 from the 60, that gives you the 40 that just read the Journal. So then they asked you to make a little table out of this. And I'm not going to duplicate the table. The table is in the textbook. A question might be, well, which of these two formulas do you use here? Formula 1, let's say, or Formula 2? Again, we're developing strategy. Think about it for a moment. And of course, this one's sort of easy because there is intersection. So you're going to use Formula 1. So basically, you could just add these three numbers together, or add the 35 plus 60, and then subtract the 20. Now, the big question is, what is our, of our 100, how many don't read at all? Well, let's see here. This looks like it's going to be so with the help of a little calculator, adding these two together, we get 95. 95 minus 20 is 75. So we have 75 out of the 100 reading newspaper articles from these papers. So the people that don't read the newspaper would be 75 from 100 is 25 individuals. Again, you can use the formulas. I like the idea that you see it laid out for you here, and it ties in with previous lessons. You're going to be doing some practice and then your quiz me's, and hopefully you'll catch on. All right, continuing on, again, we're taking this right out of our textbook. This diagram over here is what I have here. And now you see we have three sets that are going to intersect in A and B, A and C, B and C, and then here, A, B, and C. Wow. And in the text, they give you this formula, and it is a formula similar to the ones that we have up here, in which they're going to ask us, what's going on and what does it look like? Well, here, the number would be the union of all the elements in A, B, and C, which individually, the number of A, the number of B, the number of C, and now we're going to subtract the intersections of A and B C, B and C, intersections, and then we're going to add the final one of this intersection right here, and that will give us the total elements in all of these. And now for an actual example, and again we're moving into the multiplication principle. And I guess I didn't get that in there. There it is now. Multiplication principle. Okay, now we're really getting into this multiplication principle up here. And in example 3 on page 351, they talk about a product mix where they're selling a certain style of jacket, and this is the jacket, and there are 4 different sizes: small, medium, large, and extra large. And each of these come in 2 colors, blue and red. Now the question is, how many different combinations would there be if someone came in to look at these jackets? Well, that would be your outcome here. By the way, this is called a tree diagram, like a tree in a forest. And your outcomes are small blue, small red, medium, all the way down. And you might say, how many outcomes do you have? Well, in this case, there are 8 possible outcomes. Now, how did you know that? Well, you made a tree displaying your possible combinations. And you might say, do I have to make a tree every time? Well, the answer is no. And what they're going to show you now in our next little part is the mathematical way of doing this. Now, continuing, this leads to Theorem 2, where if we have, in the case of a jacket, there are 4 different sizes and 2 different colors of each jacket. This would be a 4, this would be a 2. 4 times 2 give us 8. So it depends on our operations, and then how many values are in each operation, or how many numbers. This is the general theorem then for Theorem 2. Now, for example 4 on page 352, we are wondering if we have a computer-assisted testing and there are 5 questions on the test. But for test item number 1, there are 5 possible different questions. Test item 2, 8, 3, 6, 4, 5, and 5, question 5, there are 10 different questions that will be generated randomly. And by the way, that's what we use in MathLab here. Well, keeping these different ways in mind, and we have these operations, how many different test items or how many different kinds of tests might you have all together? How many choices? And this is going to sort of astound you, I think, because the formula we're going to use is right here. where we multiply n sub 1 times n sub 2, 3, 4, and 5. These are the number in each of the ways. So we multiply this times this times this times this, and lo and behold, it tells us we will have 12,000 different tests possible. So even though there's only 5 questions, there are 12,000 possible. Can you imagine the tree that would develop in which you have these choices and then eventually this? So that's why we started you off with something real easy to show you the technique, and then we switched to the mathematical formula for actually calculating this. All right, going on to our last example, in example 5, here we're developing code words, and they ask us how many possible code words that are made up of 3 letters of the first 8 letters of the alphabet. So as you do these, they're not hard, but you need to be thinking, what are the operations, what are your sets made of? So here our set is 8 letters of the alphabet. Now, how many in each set? Well, 3. So in our first choice, we're going to have 8. And that'll be the first letter. And here, if no letter can be repeated, now here we had all of them, but now we can't repeat one of the letters, so we've used one. How many are left of the 8? Well, we can't use 1, so there are 7. Now we can't repeat either of these 2, so how many choices do we now have? And the answer is 6. So for A, it will be 8 times 7 times 6, and that'll be your answer. Now how about, again, 3 letters of the 8, but you can repeat them. So as you go along, none are excluded. So that's going to be 8 times 8 times 8. In this next one, it says of 3 letters, but the adjacent letter cannot be alike. Okay. So again, your first one is going to be 8. But now the one that's there can't be the one next to it. So how many letters do you have now? 7. And again, this letter cannot be repeated here, but this one from over there in a sense could be, so you have 7 again. So the key to all of these, and again you have to practice so you can identify what your set is, and then follow, in the case of the multiplication principle, Theorem 2. But here's where it gets a little tricky. And again, through practice, and then see the example, get some background, then try it on your QuizMe, and give it your best shot. By the way, I haven't done the QuizMes on these yet, but I have finished all of them up through 5, and I've done 7.1. So I'm going to be working on 7.2, and I mean 7.2, I did part of it, and I'll be doing 7.3 this weekend. Okay. doing the multiplication of this, we got 336. This one is just 8 cubed, 512, and this is 392. So again, lots of codes, but this is the way to figure it out. Now there's one other thing that I was looking at that I wanted to go over with you as I was doing the practice. I thought this was sort of interesting. Let me give you the technique for doing it. Now let's say we had people who were on a trip and they spoke Spanish and some spoke French, and there were some that spoke Spanish and French, and then there were some that couldn't speak either of these languages and spoke yet another language. And let's say there were 100 people on the trip. Well, let's say that 40 spoke Spanish, 30 spoke French, and we didn't know how many could speak both languages, but let's say they were 20 who didn't speak either Spanish or French. How do we find out the group that spoke the same, or that spoke both languages? Well, the first thing we would do is figure out what's our group. Well, 20 didn't speak either of these languages, and I just made up these numbers, so I don't know if they're really good or not. So actually, no, let's do this number 50 here. That's better. Because the way we do it is we have to take out our complement out of it. So the ones that speak both are 80. Or that speak a language are 80. So now what we have to do is we're going to go 40 plus 50 minus this group in the middle here, which is going to be n, and that's going to equal the 80. How did we get the 80? Well, we subtracted the 20 who didn't speak either of these languages from 100, which was our total group on the trip. So we then find that we have 90 minus n equals 80. Subtract 90 from both sides, we get a negative n equals a negative 10. So n equals 10, and that's our group here that speaks both Spanish and French. And that was one of the quiz me and practice questions, and I noted that we hadn't gone over it. This is from the first part of the addition principle. I didn't do the multiplication yet, so I may come back with something to add later. Okay, that'll wrap it up.